Students, welcome back to part 2 of lecture number 20. So, we are discussing about data warehouse. This is in a nutshell what I talked about it. It is a multi-tier architecture. You have three things: data sources, data storage, OLAP engines, and obviously front end tools, right. So, in case of data sources, you can have different kinds of databases which are created, and then you have what is known as a data warehouses. That is where you keep the data. It can be metadata or it can be original data, right. Data, sometime you can call it data marts. You can see here, like these are like markets where data will be sold, and then it will be used in a OLAP server. Okay. I hope you remember OLAP. OLAP is online analytical processing. Okay, that is what you can click and process your data, right. So, OLAP servers will allow you to analyze the data in a terms of very systematic manner, and then the front end you can provide your query or report or data mining things. Okay. That is what is done in a front end business. Okay. Remember that. So, front end is something which is not very important, but the end OLAP engine does most of the work. Okay. So, this was going to be the futuristic view of data warehouse. It is going to happen in the next 5 to 10 years. So, what are the objects, data objects? Obviously, data objects are made of entities, like in case of sales databases, customer ID, store item, sales. Medical databases will have patient statements. University databases, like our cases, will have students, professors, courses. In case of material databases, you can have properties, like mechanical properties. You have different kinds of properties, functional properties. You have catalytic properties, sensor properties, okay, and electrical properties, electronic properties, like that. You can also have the data objects will be always described by attributes. Attributes are basically features, right. That is what I talk about. Let us talk about patients treatments, they are also attributes, customer is also attribute, properties are also attributes, right. So, that means rows will have data objects and columns will have attributes. Remember this, that is how the data must be created. And attributes are like data fields, like you can have simple example is customer ID, name, address, students roll number, name, address, right. Courses, the name of the course, how many students enroll in the course, like that. Okay. How many are taking the exams, these are called attributes. Sometimes they are also called features or variables, I told you, right. So, attributes are used as a glorious term, but better to use features or variables. There can be different types, nominal types, like the ones we talk about it. It can be binary type or it can be numeric type also. So, in case of numeric type, it is a quantitative, then you have interval scale or radius SEO scale also possible, all kinds of scaling is possible. Let me tell you, I am giving only 2 examples, numerical aspects, but there are 3 types of things possible: attributes, nominal, binary, and numeric. So, you can always initial analysis of data you can do by central tendency, that is nothing but statistics like mean, median or mode. I do not want to give all the details of that, you can read from the slide. So, mean is basically either weighted arithmetic mean or it can be trim mean, you can chop off the extreme values. So, you can see that different definitions are given here on the slides. Weighted means at Wixi by summation of Wi, and simple mean is basically what 1 by n summation of x, right. That is what it is. So, median is what it tells you middle value, if the odd numbers of values, average of the middle 2 values also takes about it. Okay. And it can be used calculated by simply interpolation, like given here L1 plus n by 2 minus summation of frequency divided by frequency median into width. Okay. That is what is median. Median tells you the middle value. Okay. Mode tells you the, let us say mean tells you the average value, and mode tells you which is the most widely frequently observed data. Okay. Most frequently observed data. It can be unimodal, it can be bimodal, it can be trimodal, and this formula you can use mean minus mode is 3 into mean minus median. So, if you calculate 2 of these parameters, you can calculate the third one. You need to do that. So, this is what you can see is the age versus frequency. So, this age group is the highest frequency, right, that is your mode. Okay. Am I clear? Rest are actually less, 21 to 50 is what is the highest frequency age group. You can also visualize data, I talked about it, let me just put it together. You can have geometric transformations and visualization, direct visualization, scatter plots, landscapes, hyper slides, all kinds of terms you are seeing, you will be can see in the internet to look at it, but mostly we can use square for scatter plots and other matrices, and direct visualization also use. So, next 10 minutes or so, I will talk about some bit of mapping of materials. Okay. So, materials are generally described by their their properties, right. That is what you do as structure, that is the main capability things. Let us first talk about what is mapping with materials machine learning. Okay. So, visualization of complex data sets is very important, right, as we have seen in the last few lectures, and this is important because we have to make informed decisions. Finally, you are going to make decisions out of your data analysis. So, that is why it is required to use visualizing the data, since it is used to represent the spatiotemporal spatial information effectively. So, the process which is involves identifying and linking these AI models to the respective data sources, and also understanding the pathways through which data has been processed and transformed, so that it can be connected. It is what is known as a mapping. Okay. So, you identify, link the data with the AI models, understand the pathways through which the data has been processed, transformed, visualized, that is what is done in mapping. So, these are very crucial in transforming the complex data to easy to understand things like visual formats, plotting of data, okay, like a geographical or spatial elements. This helps in interpreting different kinds of things like trends, undiscovering hidden insights, okay, many cases, facilitating decision making processes across various industries. That is why mapping is so important. So, what mapping does is basically transform the complex data into a presentable things, whether it is like a plot or whether it is like a map or it is like a spatial element kind of things. It provides you clear representative of trends, first important things. Maps usually displays trends, make it easier for us to understand. Maps also allows you to uncover hidden insights, something which may not be able to see from data. When you look at data, you can thousands of data, how do you understand what is hidden insights? So, mapping allows you to reveal these insights, and that is the key, understands and it enhances our understanding of the complex problems. Many cases it aids a regional analysis like climate conditions, economic development, material behavior, customer preferences, all kinds of things it can provide regional analysis. Okay. And in the first three of things like trends, hidden insights and regional analysis provides you improved decision making capability, because if you are doing accurate jobs, this will allow you to plan resource allocations, risk managements, many other things, and obviously globally it can provide you enhanced collaborations. Once you have a various kinds of diverse things, it is possible to make enhanced collaboration. Okay. So, these are the 5 important things mapping allows you to do. So, let us talk about material science mapping, how it is. Normally materials mapping is done using deep learning approach, which we have not discussed in our course, but let me discuss about this also. So, as you know, material science is a broad discipline, and here your material processing is related to structure related to properties. So, can I actually connect this and make a map out of it? This is taken from this paper of Hashimoto et al, which is in archives, you can access that. As you know, there are thermoelectric materials which convert thermal energy into electrical energy, correct. If you do not know, you can look at literature. These materials actually convert thermal energy into electrical energy. So, a lot of heat is dissipated during a operation industry. You can take the heat and convert into electrical energy. One of the parameters which provides you the comparison how the material behave in terms of conversion of thermal to electric energy is what is a ZT, and ZT can be experimentally measured obviously, and it depends on particular material compositions, processing conditions and many other aspects. You can also get these ZT values from computational data sets also, like you can also calculate it from various kinds of computational aspect like DFT calculations, MD simulation also. So, therefore, you get all this data as input. You can have images also, because material structure of material is always provided as images, as you know. So, properties are fundamentally linked with the underlying composition and structural arrangements of the atoms, right. So, address this problem, we can normally resort to this graph or graph based tools, which is shown in this slide also here, you can see that, and so that we can actually get a lot of information out of it. And this is done using what is known as a convolution neural network methods or graphical convolution network. GCN is what is called graphical convolution network. It is basically based on ANN, but it is allowed to handle, but made in such a way it can handle a lot of images. There you have pooling data, dense layer, output, this is all there in my course in AIML, materials engineering, you can get it. And from there you can actually create hundreds of dimensions and reduce it to dimension 2 dimensions and plot it like this, and then this is the predicted ZT. You can see the heat map basically kind of stuff. So, this is one such map I am showing you for your understanding. You need to get into more details how these material maps are done. You don't need to get into details of that at this moment. You must have an idea how material maps are important, why it is coming into picture. Here color of each data point represent the predicted experimental ZT values. Okay. This is the predicted experimental ZT values. You can see here you have a gallium silver selenide, you have a cobalts antimonides, terbium selenides, niobium selenide antimonides, bismuth tellurides. These are the classical materials used for thermoelectric application. That is why we have used these things. So, position of P data point reflects the structural properties of material extracted by this model called mapping deep learning, mapping based deep learning. And there are two branches which is like this, spreading laterally at BR1 and BR2 in the map. Structure of Bi2 Te3, that is what it is shown here, and gallium silver selenide are demonstrated to illustrate different complexities of these two branches. You can see there, these are the two reduced dimension methods. So, once you collect a lot of data and make a CNN, GCN type of model, you are going to have data in terms of large dimensions, sometimes you can go up to 100 dimensions, 100 different features. So, you can handle that. So, that is why you have to do dimension reductions, and many times it is done by Pearson correlation coefficients, and then you have 2 dimensional data and plotted like this. This provides a lot of information. You can clearly see for Pi2 Ti3, these are the things which is high ZT 1.2, 1.1.0 or something. The green ones or blue ones as low ZT, which are not very useful. That is what you can read. So, this maps provides you across the whole spectrum how to select a best thermoelectric material. That is what I am talking about it. So, this is what it looks like. Let us talk about another one. This is the atomic scale imaging to material property connections. Atomic scale imaging of materials is widely used, what is known as high resolution transmission electron microscopy. And in doing that, we can actually get information about each atomic column. That is what is shown here. This is high angle annular dark field image, high angle dark field image. From there, actually you can create a zoom view and you can extract, remove the noises and extract information out of it. Once you have the segmented image, which is created at the bottom after removing all the noises, any kind of microscopy tool have lot of noises. You have to remove the noises using the new noises by using deep learning tools. So, and then you can get a segmented image, very nice colored image you can see. Now, you can use the segmented image to do k-means clustering, find the center of masses, find A and B time atoms very easily. You can know what atom is what, which is not possible in normal high resolution microscopy imaging. You can also do segmentations, you can remove some atoms, A atom let us say remove and have only B atoms, then you can do K-mean clustering to understand what kind of arrangement of atoms are there. And you can use this arrangement of atom directly predict the properties, because properties will depend upon the how the structure is developed, right. That is what is done normally. So, this is a new field which is catching up very widely, and this is what is called grouping by block matching. You can see these are the block match, different blocks are done, you can group it together and then you can do analysis to find out. You can use either collaborative filtering techniques to create real images, okay, it is shown here. This is pumice strontium titanate, this is very widely studied material. So, am I clear? So, this is how actually the maps to material properties can be done. So, you know the material structure very easily, you can read it from images and from that images you can develop the models for predicting properties. Am I correct? That is the what is known as the link between processing structure property, or it is called PSP. That is the ultimate goal of many material scientists. So, we are not going to talk about in details of that, because that will require several lectures, but I just wanted to provide. So, let me just go ahead about I think this we discussed about it, or you are going back, I do not know. So, let me just go to the end of the lecture, and I have finished my portion of lectures 1 to 20. So, lecture 21 Professor Pratik Ray from IIT Ropar will start discussing with you, and so you can look at it other aspects of the course, like at the beginning I shown you, and understand that. So, with this I would like to thank you for your presence and sincere interest in this course. Thank you.